This image just dropped. It's a raw capture of 3i Atlas shared publicly exactly as recorded. No cosmetic cleanup, no heavy processing, no artificial enhancement. A 12-inch Dobsonian telescope, an EQ platform, a consumer-grade IMX 410 camera. And yet a directed feature is already visible, not teased out later, not invented in software. Present in the raw frame itself. That's why this image matters. This is the raw color frame. No contour overlays, no contrast stretching, no directional arrows. What you're seeing is the light distribution exactly as the sensor recorded it. The central region stays compact. Brightness falls off smoothly in every direction except one. There's a subtle asymmetry here. A slight bias in intensity, not sharp, not exaggerated, but real. This is before anyone tries to find a feature. And that's the key point. Even at this stage, the structure isn't perfectly symmetric. Now, the same data is viewed through color separation. Nothing added, no sharpening. Just the channels weighted differently. So contrast emerges. And this is where the structure stops. Being ambiguous, the central core remains compact, but one side darkens and stretches outward. Not randomly, not symmetrically. That darker wedge isn't noise. Noise scatters. This stays coherent. It points in a single direction. When different color channels agree on the same geometry, you're no longer looking at a processing trick. You're looking at directionality. This is the same frame again, but inverted and pushed to reveal what normally hides in the background. No smoothing, no cosmetic cleanup. And now the geometry locks in. The core stays tight, but the extension doesn't dissolve into grain. It sharpens. Noise breaks apart when you invert it. Real structure survives. This survives. You can trace a single direction from the core outward even as the surrounding field turns chaotic. That's the key detail. Not brightness, not color, direction. Across raw, collaborated, and inverted views, the same feature keeps reappearing. That's not processing. That's behavior. This next frame is different. This isn't a single exposure. It's a stacked analysis built from 61-minute frames captured on December 15th, 2025 from Tony Scarato's observatory in southern Italy. Same object, much deeper look. What you're seeing here is the same data split into separate color channels. Red, green, and blue, and then processed independently. That matters because noise behaves differently in each channel. Real structure doesn't. Top left is the reference image. The object tracked against your background stars with orientation marked that. Establishes motion and direction. Everything else builds on that. Now look at the red channel. This is where the Larson's second filter is applied. A technique specifically designed to reveal rotational and radial asymmetries. And what comes out is not a diffuse glow. It's a directed extension, emerging cleanly from the core. The circled region marks the nucleus position. The structure extends away from it coherently. Switch to the green channel. Different wavelength band, different noise profile. Yet the same feature reappears, same origin point, same direction. The intensity changes as expected, but the geometry stays locked. That's critical. Now the blue channel. This is usually where structure falls apart first. Shorter wavelengths amplify noise. But even here, the extension doesn't vanish. It weakens. But it doesn't rotate, scatter, or randomize. 3 channels. Different wavelengths, different processing paths, same direction. And here's the scale that matters. At this distance, 1 pixel equals about 3,850 kilometers. So, this isn't a tiny artifact. This is a large-scale feature extending tens of thousands of kilometers from the core. When a structure survives stacking, survives channel separation, and survives aggressive filtering, it stops being a processing curiosity. It becomes behavior. This next image pushes the timeline much further. What you're seeing here is pulled from a 3-hour time series run. 180 minutes of continuous tracking, not a single snapshot. Same object, much longer baseline. The key detail isn't brightness, Its consistency across 180 separate 1-minute exposures. The object keeps the same compact core and the same asymmetric envelope. If this were random cloud interference, tracking error, or transient noise, the shape would smear out over that time scale. It doesn't. Notice the background stars. They're slightly trailed, which tells you the telescope is locked onto the object itself, not the star field. That means all internal structure you see is intrinsic to the object, not a motion artifact. Ira explicitly notes something important in his caption. The frame brightness fluctuations are random cloud cover, not activity spikes. In other words, the noise varies, but the geometry does not. That's a quiet but powerful constraint. At this point in its trajectory, the object is moving at roughly 130,000 miles per hour relative to Earth. Over 3 hours, that's a significant change in position. Yet, the internal structure holds together. No fragmentation, no rotational blur, no chaotic spreading. Longer time baselines are where false features die. This one survives. So now we have short amateur exposures, multi-channel filtered stacks, and a 3-hour continuous time series all pointing to the same conclusion. This object structure is persistent, not momentary. Let's slow this down and look at what the data from mid-December is actually telling us across observations taken between December 15th and 18th. The same feature keeps showing up. Not after aggressive processing, not after enhancement tricks, right there in the raw frames. A directional jet emerging straight from the central region. What matters here is not just that the jet exists, it's that it appears before any cosmetic processing is applied. That immediately rules out filters, contrast stretching, or post-processing artifacts as the source. Now, look at the core itself across different exposure lengths, different cameras, and different nights. The central region stays compact. No smearing, no breakup, no diffusion you'd expect if this were unstable or fragmenting. The geometry holds. Even more telling, the orientation of the jet doesn't wander. Multiple observers, different instruments, same direction. That's not coincidence. That structure, when the data is split into red, green, and blue channels, the feature doesn't disappear. It persists across wavelengths, which tells us this isn't a single band noise effect or a sensor glitch. In long-time series sequences over 3 hours in some cases, there's no fragmentation, no collapse, no chaotic spreading, just steady behavior. And critically, the background stars trail while the object stays sharp. That confirms object lock tracking. This structure is real in the sky, not in the software. So when you put all of this together, time, wavelength, independent observers, you get the same result. The structure persists, and that's the part that deserves attention. So here's the real question to sit with. If this jet is visible before heavy processing, holds its shape across time, and stays aligned across multiple observers and wavelengths, what exactly is driving it? Is this just an unusually active nucleus behaving at the edge of what we expect? Or are we watching a process we don't fully understand yet? Let me know what you think in the comments. I read all of them. And if you want to keep tracking 3i Atlas as new data drops, hit like, subscribe, and share this with someone who's been following the story. More images are coming.